The Common Language Specification, commonly known as CLS, is an important part of the .NET architecture that ensures language interoperability. In the .NET ecosystem, many programming languages such as C#, VB.NET, and F# can be used to build applications. While these languages differ in syntax and features, they all run on the same runtime environment called the Common Language Runtime, CLR. The challenge arises when code written in one language needs to be used by another language. CLS was introduced to solve this problem by defining a common set of rules that all .NET languages agree upon. CLS acts as a contract between language designers and developers. It specifies a subset of features from the Common Type System, CTS, that are guaranteed to be supported by all CLS-compliant languages. While CTS defines everything that is possible in the .NET type system, CLS defines what is safe and common for cross-language usage. This distinction makes CLS extremely important for building reusable libraries and frameworks. Before .NET, combining multiple languages within a single application was difficult. Each language had its own data types, naming conventions, and runtime behavior. Even when languages ran on the same operating system, interoperability required complex wrappers and adapters. CLS eliminates this complexity by enforcing a shared set of rules that all languages must understand and support. When a developer creates a .NET application using a single language, CLS rules may not appear important. However, when building class libraries, APIs, or shared components, CLS becomes critical. A library written in C# might be consumed by VB.NET or F#. If the library uses features that are not supported by those languages, compatibility issues occur. CLS ensures that such problems are avoided. The CLS does not define new types. Instead, it selects a subset of CTS-defined types and rules that are universally supported. This means CLS is not a replacement for CTS, but rather a compatibility layer built on top of it. CTS is broader, while CLS is stricter. One of the primary objectives of CLS is language interoperability. This means code written in one language should be easily used by code written in another language. To achieve this, CLS defines rules for naming, data types, visibility, inheritance, exceptions, and method signatures. CLS enforces consistent naming conventions. For example, CLS requires identifiers to be case-insensitive. This is because some languages, such as Visual Basic, are case-insensitive, while others, like C#, are case-sensitive. If CLS allowed case-sensitive identifiers, two methods with the same name but different casing could cause conflicts in some languages. Therefore, CLS prohibits such usage for public members. CLS also restricts certain data types. For example, unsigned integers are not CLS compliant. While C# supports unsigned types such as uint and ulong, not all .NET languages support them. To maintain compatibility, CLS advises developers not to expose unsigned types in public APIs. Similarly, CLS restricts the use of pointers. Pointer types are allowed in CTS but not supported by all languages. Therefore, pointers are not CLS compliant and should not be exposed in public interfaces. CLS requires that all public types and members be accessible using standard naming rules. It discourages the use of language-specific keywords or symbols that cannot be represented in other languages. Method overloading rules are also governed by CLS. CLS does not allow method overloading based solely on return type. This is because many languages cannot differentiate methods by return type alone. To maintain interoperability, method signatures must differ by parameter types or parameter count. CLS also defines rules for exceptions. All exceptions that cross language boundaries must derive from system exception. This ensures that an exception thrown in one language can be caught and handled in another language without issue. CLS enforces accessibility consistency. If a method is public in one language, it must be accessible in all other CLS-compliant languages. This prevents unexpected access restrictions. Another important CLS rule relates to inheritance. CLS requires that inherited members behave consistently across languages. Virtual methods, overrides, and interface implementations must follow standard patterns defined by CTS and approved by CLS. CLS also defines rules for enums. Enumerations must be based on a CLS-compliant underlying type. This ensures that enum values are interpreted consistently across languages. CLS-compliant libraries must also avoid exposing nested types in complex ways that may not be supported by all languages. CLS strongly encourages the use of attributes such as CLS-compliant true to explicitly indicate whether an assembly or type follows CLS rules. This attribute helps developers identify whether their code is safe for cross-language use. When CLS-compliant true is applied, the compiler checks the code and generates warnings if non-CLS compliant features are used in public members. This makes it easier to build interoperable libraries. CLS compliance is especially important for framework developers. Libraries intended for wide usage must be CLS compliant to ensure maximum compatibility. The .NET base class library itself is largely CLS compliant for this reason. CLS does not restrict private or internal code. Developers can freely use non-CLS compliant features inside their implementation. CLS rules apply only to publicly exposed members. This allows developers to benefit from advanced language features internally while maintaining compatibility externally. This balance makes CLS practical and flexible. It does not limit language innovation but ensures interoperability at boundaries. CLS also plays a role in versioning. Because CLS enforces predictable behavior, changes in public APIs are less likely to break consumers written in other languages. In real-world development, CLS is most relevant when creating reusable components, SDKs, NuGet packages, or shared enterprise libraries. Application-level code may not require strict CLS compliance, but shared libraries should always follow CLS rules. CLS also improves maintainability. Developers working in different languages can understand and consume shared components without confusion. From an architectural perspective, CLS helps .NET achieve its goal of being a truly multi-language platform. Without CLS, language independence would exist only in theory. CLS makes it practical and reliable. CLS works closely with metadata. The CLR uses metadata to understand type definitions and enforce CLS rules. Compilers generate metadata according to CLS guidelines when compliance is enabled. CLS also simplifies tooling. IDEs, debuggers, and documentation tools rely on CLS-compliant metadata to provide consistent behavior across languages. Although modern .NET development is dominated by C#, CLS remains extremely relevant. Many organizations still use multiple .NET languages, and public frameworks must remain language neutral. CLS also improves developer confidence. When developers see that a library is CLS compliant, they know it can be safely used regardless of language choice. The relationship between CTS and CLS can be summarized simply. CTS defines all possible types and behaviors in .NET. CLS defines the safe and common subset that guarantees interoperability. CTS is wide, CLS is narrow. CTS allows, CLS restricts for compatibility. In summary, the Common Language Specification is a crucial component of the .NET architecture. It defines a standard set of rules that ensure code written in one language can be used by another language without issues. By enforcing consistent naming, type usage, accessibility, and behavior, CLS enables true language interoperability. While developers may not interact with CLS directly every day, it plays a vital role behind the scenes. Understanding CLS helps developers design better APIs, create reusable libraries, and fully appreciate the multi-language power of the .NET platform.